Assalamualaikum everyone. We are still in topic 7.3 Synchronous Counter Design for subject Digital Electronics. For this video, we're going to look at how we can analyze a synchronous counter. Okay, for this topic, we're going to look at how we can do the reverse process of counter design. Okay, we're going to do the reverse process of counter design. So for this purpose, there are 3 steps. Okay, based on the first one, based on the counter circuit given we are given a counter circuit. So we want to understand that counter circuit. What is going on? What is the inputs? The counter circuit, and what is the sequence of that counter circuit, how it counts, how is the counter circuit is counting, whether it's counting from 0, 1, 2, 3, or maybe 1, 3, 5, 7, or whatever the sequence is. So we're going to analyze that counter and try to decode and find out the sequence and the states of that counter. Okay, so the first step is we write the equations for the J and K inputs for each flip-flop. And then the second step, we're going to generate the counter transition table. And finally, we're going to draw state transition diagram. And eventually, we're going to look at the waveform. All right, so let's look at an example. Let's say we are given this synchronous counter. Okay, how do we know this synchronous counter? Look at the clock. Okay, so look at the clock. They are all connected into one common clock. So it's a synchronous counter, and looks like it's an NGT flip-flop because of the presence of a bubble here, right? And look at the inputs of each flip-flop. Flip-flop C, for example, J is connected to this AND gate, and K is connected to C. Okay, so those are the basics information that we can get from a given counter circuit. Right, and flip-flop B, where is J and K connected to? And flip-flop A, where are the inputs connected to? Okay, so those are the things that we're going to investigate when we get a circuit like this. Alright, so then the first step is to write the equation for J and K input for each flip-flop. So let's do this one. So for the first one, A flip-flop, look at the J and K, they are both connected to the C bar of flip-flop C. So J and K is equal to C bar. Settle, we're finished for flip-flop A. What about flip-flop B? Flip-flop B, if we trace the J and K inputs, we can see that both J and K inputs of flip-flop B are connected to A, output of flip-flop A. So J and B of flip-flop B is equal to A. And what about this one? This one, there's an AND gate there. So we trace the connection of J for flip-flop C, and looks like it is connected to an AND gate, and the input of that AND gate is A and B. So we simply put JC is equal to A dot B. Okay, and finally flip-flop C, the K input is equals to C. So just like that, now we have all the equations for the J and K inputs for each flip-flop that we have. All right. Now the next step is to generate counter transition table. It's the opposite of what we did when designing a counter. So in this case, we have the present state, okay, based on the equation that we have previously. We try to find out, or we try to populate this table with the correct combination of J and K control inputs. Okay, so let's look at the first one. Let's look at this one first. J and K for C. Okay, so for J, K for C flip flop. Question is, let's look at J first. J is A dot B. Okay, so A dot B. So which means that J will be, the output of J will be 1 if A and B are 1 also. Okay, so look at the present state table column here and find out where is the A and B 1. So here, so that means here A will be 1, and also here A is 1, B is 1. So here J, C will also be 1, and the rest are 0. Okay, because JC is A dot B. What about KC? KC is very simple. KC is equal to C. So in the when the present state is C is 1, K is also 1. Okay, and the rest is 0. Okay, so that's how we populate this table. So what about flip-flop B? Flip-flop B, J and B, JB and KB, sorry, JB and KB is equal to A, which is much easier lah. Whenever A is 1, here, 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 and here, the J and B, JB and KB of flip-flop B is also 1. Okay, this is the easiest lah. 1, 1, and then here, 1, 1, and here 1, 1. The rest are 0, 0, 0, 0, 0, 0. Okay, and finally for JA and KA is equal to C bar. So wherever in the present state C is 0, so both JA and KA are 1. Okay, 1, 1, 1, 1 here, and the rest is 0. All right, so that is the control inputs condition for our present state. Okay, here's a better look at the table. All right, now that we have this table, next is we're going to add another column here, okay, next to the FF control input, which is the next state, right? Remember, when trying to generate the counter transition table, in this case, we already have the present states and the FF control inputs. Now we need to find out what is the next state with this counter. Right now, let's try to do T first. Okay, now to do this, we have to refer back to our JKFF excitation table to predict the next the next state, sorry. Now let's look at the first row and do the C first. So the present state is 0, okay, and J is 0, K is 0, all right? So it's either this one or this one, and J is 0 and K is 0, so we take this one, okay, because for present, when present state is 0, it could be J0 or J1. In this case, J is 0, so we take the next state as 0, right? What about B? Let's look at flip-flop B. Flip-flop B is 0, present state is 0, and the JB, KB is also 0, 0. So it looks like it's same. which means the next state is also 0. And finally, for flip-flop A, okay, flip-flop A, the present state is 0 again, either this one or the second row. And the input, control input is in this case 1, 1. Okay, so it's 1, 1. So J is 1. So we're going to use this row, right? And the next state. Therefore, we put the next state as 1. Okay, so we continue to populate. We go row by row, and uh, we can also go it column by columns. Let's say you do C first, and then you do B, and then do A, and finish up this table so that you get this complete counter transition table. Okay, and when you have finished that, the next step is to draw the state transition diagram and finally the waveform. Okay, so how do we draw this state transition diagram for this counter? Look at the pattern of this counter. Okay, it looks like this counter counts up by looking at the table. You can see that the counter counts up to 0, 1, 2, 3, 4, and then in the next state, after 100, the next state is back to 000. Okay, so when we see that the counter goes back to the first condition, so that means this counter counts up to only 100, and then it will repeat back to reset back the counter, right? So how many states do we have? 1, 2, 3, 4, 5. So we have 5 states. So let's put the states first. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and finally we have 1, 0, 0. Okay, so the next step is to connect the states. All right, in this case, 0, 1, 0 goes to 0, 0, 1. Okay, and 0, 0, 1 goes to 0, 1, 0. And 0, 1, 0 goes to 0, 1, 1. And 0, 1, 1 goes to 1, 0, 0. And finally, after 0, 1, 0, 0, it goes back to 0, 0, 0. Okay, so we have finished all the cycle. Now look at the three last row. Okay, the three last rows of this table. These are unused states. Okay, and for this counter, 0, 1, 0, whenever the counter comes to 101, it will change its condition to 011. So therefore, 101 we put near the 011 here. Oh, let me change the color first. Okay. 101, whenever the counter sees or encounter the number 101, it will force the counter will be forced to go to 011, and 110 will go to 010. So here is 110, it will go to 010, and finally 111 will go to 001, 111 to 011. So that is our state transition diagram for this counter. Finally, we draw the state transition diagram, and we have drawn the state transition diagram, and finally we can draw the waveform based on the table. Okay, remember it's an NGT flip-flops. We're using NGT flip-flops, so all the transition will happen at clock transition from high to low. Right, for C, for example, for flip-flop C, it goes high here, and B, uh, second clock cycle goes high, and for A, just follow the what we call the table, the flip-flop table here, and just follow whatever the output here. And we get our state, our waveform for our counter. Okay, so that's how we can analyze a counter. Okay, so that's it for this video. Thank you very much for watching. Bye.